You're tuned in to the Data Masters podcast. In each episode, we dissect the complexities of data management and discuss the data strategies that fuel innovation, growth, and efficiency. We speak with industry leaders who share how their modern approaches to data management help their organizations succeed. Let's dive straight into today's episode with Anthony Dayton.
Welcome back to Data Masters. If you've ever written import pandas as PD in Python, then our guest today needs no introduction. He is the creator of Pandas, the seminal open source library that practically defined Python as a language for data science. But he didn't stop there. He's also the creator of Apache Arrow, creating the de facto standard for how high-performance systems exchange data, in particular tabular data, and is currently a principal architect at Posit, the chief scientist at Voltron Data, and a general partner at Composed Ventures. Wes McKinney has spent nearly 2 decades building the foundational infrastructure that powers our industry. And today, we're going to talk about what comes next, from the rise of the composable data stack to his contrarian view on why LLMs might be heading for a trough of disillusionment when it comes to actual analytics. Wes, welcome to Data Masters.
Thanks for having me on the podcast.
So I wanted to maybe start by going back in history a little bit. And I know this is almost an unfair question to sort of cast your eye back 15 years ago when you started the Pandas project. But I think it's fair to say, and again, with the benefit of hindsight, that it really, it built this Python-based data science ecosystem. And in that sense, Python has become the de facto standard for a whole bunch of AI platforms, TensorFlow, PyTorch, et cetera. So I'm just curious from your vantage point, sitting here today, looking back, if when you were first building Pandas, did you have a sense that it would become the sort of foundational layer for AI?
It would be hard to predict that far into the future, but I think I definitely saw there was a lot of untapped potential in Python, and if only there was a toolkit for basic data manipulation, data wrangling, then that would help unlock whatever was the potential or potential future for Python as a mainstream data language. But back in 2008, when I started working on Pandas, it was not at all the case and was not a foregone conclusion. Even using Python for doing professional business data work was seen as fairly risky at the time because Python was unproven. It had a fairly immature open source ecosystem for statistics and data analysis work. And the idea, initially Pandas started out as a toolkit for myself to do my work at my job at a quant hedge fund. And I enjoyed building the toolkit for myself. And then eventually I was building it for my colleagues who were excited about using it. And eventually we open sourced the project and I started engaging with the Python community and seeing is there an appetite for this? Do people want this? Is this something that the world needs? And eventually it turned out that the answer was yes, that it was at a little bit being at the right place at the right time around 2011, 2012, where people were starting to talk about data science and big data. And there was suddenly a massive need for people with data skills. And Python was an open source, accessible programming language that people could learn easily. And the sudden availability of a toolkit to be able to read data out of databases and load CSV files and read Excel files and then be able to do meaningful work with that data with code that was easy to write and easy to reason about was one of the things that helped unlock Python as a language that could be accepted in the business world. And I don't know if this was causal or something that really factored into Google choosing Python as the language for TensorFlow. I think it was a little bit of an accident. I was partly inspired by the fact that Google used Python as their one of their 3 languages, the other 2 being C++ and Java. So Python was their scripting language that they would use to build interpreted interfaces on top of mainly C++ libraries using Swig and other wrapper generators. So that was probably the main reason why Google chose to do TensorFlow in Python. And eventually Meta started building PyTorch. Initially Torch was all in Lua, I believe. And eventually they migrated that to to Python to create PyTorch. And so there's a combination of like being lucky and making the right prediction, but also this lucky confluence of combination of open source projects and then major AI research labs needing to choose a programming language to build their AI frameworks in. It just happened to be that everyone chose Python. And so, we were all rolling around our little snowballs, and suddenly the snowballs merged together and became one really gigantic snowman that now powers the world. So it's been an interesting time, but I've been resistant to patting myself on the back and saying like, oh, I predicted this was going to happen. I knew it was going to end up like this, because that's definitely not the case. I was hopeful that things would end up like this, but I would have been satisfied with a much less successful outcome.
So I can pat you on the back. So how about that? So I think that's fair. In that same spirit, though, and maybe this is an unfair question, but just to throw it out there, were there other features of Python that lent itself? Clearly, you solved a big unmet need around access to data and also munging that data, to use your term. But were there other features of Python that made it particularly relevant for this use case?
I think because Python is really easy, was originally created as a teaching language, so it's easy to learn, it's easy to read. People back in the day would often describe Python as readable pseudocode, like similar to the code that you would write to describe algorithms. So you could hand a piece of Python code to somebody who'd never written Python before, and they would pretty much be able to get the idea of what the code was doing without a lot of like types. And of course now Python has types, and so that's changing. But the language had an accessibility and a readability aspect that made it really appealing to do scientific work in. Python also had an existing numerical computing ecosystem. So there was a group of folks that were essentially building an alternative to working in MATLAB. So if you were doing neuroscience research or physics research or things like that, you had NumPy and SciPy as a basic computing foundation for numerical algorithms, optimization, linear algebra, the essential things that you would need to begin to start doing statistics and data analysis work. Like whenever I needed to run a linear regression in Python, I didn't have to wrap linear algebra libraries myself. Like that work was already done. So that was an essential factor. I think another thing that really helped tie the room together was the computing and development environment, which initially started out as being the IPython shell and eventually the IPython notebook, which turned into the Jupyter notebook and now the Jupyter ecosystem and Jupyter Lab. And so that also gave people, that was one of the first mainstream open source computing notebooks. People were familiar with Mathematica and other closed source computing notebooks in the past, but this one was inspired by things that had come before out of Mathematica and MATLAB and things like that. But it was open source and just worked with Matplotlib, the plotting libraries, and all the things that existed at the time. So essentially, very quickly by 2013 or so, we had this full stack environment that had the bare essentials of a interactive computing environment through the IPython notebook, Jupyter, numerical computing through NumPy and SciPy, plotting through Matplotlib, and data wrangling through pandas. And so if you were an aspiring data scientist or somebody who was looking to do business analytics or some type of build a data analysis application in a business setting, at that point you could credibly make the case to your colleagues and your boss or whoever that you had the tools at your disposal to be able to build something without getting pulled down into a rabbit hole, having to like build essential components from scratch. I mean, some people underestimate like how important it is to be able to read CSV files, but it turned out that like just being able to point pandas at a CSV file was its initial killer app. Like, oh, I have a data file, I can say pd.read CSV and read it. People take that for granted now, but in circa 2012, like that was a big level up for Python at the time.
No, I mean like that alone. I mean the hell that is parsing CSV files. Being able to abstract that away and deal with the common use case there is, and probably I would venture to bet 98% of use cases were loading CSVs off a local file system, even for very large amounts of data. Uh,
Yeah, absolutely.
so shifting to the more closer to the present, and you've also shifted your energy and focus towards Apache Arrow, and I think it would be fair to say that you would frame Arrow as the foundation for the composable data stack. And there's tools like DuckDB and others that are sort of based on that. So talk a little bit about what the composable data stack is for those that are not familiar, and maybe building a little bit on these lessons you talked about, building the bigger snowball, this idea of interoperability and building an ecosystem, and how Apache Arrow fits into that as well.
Yeah. So, well, you can think about the late 2000s, early 2010s as being a little bit of like the food, water, and shelter era of big data and open source data processing in general. And so you had disparate communities building solutions to solve the immediate essential problems that were right in front of them. And so there was relatively little consideration to building, larger, more heterogeneous data stacks full of multiple programming languages, different data analysis tools, processing engines, storage engines. And so people were in general building vertically integrated systems where they would build a solution for a particular problem with a layer of technologies, where classically you would have a database system that has everything tightly integrated together. So the storage engine, the data ingestion, query planning and optimization, query execution, as well as the SQL front end, and that would all be present within a full stack, a vertically integrated full stack system. But one of the key ideas from the Hadoop and big data era, which was originally kicked off by Google's MapReduce paper, this idea of disaggregated storage, or storage being decoupled from compute. And so you could start to think about, okay, how can we store data in a way that multiple compute engines can work on it? So that gets you thinking about standardizing data formats, so having open standards, open source standards for data formats. And that was stage one of what was happening in the big data ecosystem. But as time dragged on, there was a collective realization in the mid 2010s that the cost of building one-to-one interfaces, like pairwise interfaces between programming language A, computing system, or storage system B, was not only hampering the performance of systems by introducing a lot of serialization and interoperability overhead, but was also fragmenting effort and weighing down progress in the overall open source data ecosystem. So the original idea of Arrow was, if we could define an open standard for data interoperability for tabular data, in particular column-oriented data, similar to what you would find in pandas or in an analytic database, and we could use that format for moving data efficiently between programming languages, between compute engines, between storage systems and execution layers. And that would not only improve performance, but also reduce the amount of glue code that has to be written by developers to make these systems work. And so we initially started with this data interoperability problem of essentially having a better wire protocol for hooking together systems. But what was interesting is that once that that came through the Arrow project, we already had some standardized file formats like Parquet and ORC at the time, and Arrow was designed to work really well with those as a companion technology. But what we've seen as time has moved on is that we can start to modularize and decouple the other layers of the stack, and so we can start to think about modular execution engines, or decoupled front ends, like different types of user interfaces for interacting with compute engines, not only SQL, but also more data frame-like interfaces like what you would see from using pandas. And so the kind of the way that we described this, like composable data stack, another way that we looked at it was deconstructed database. So if you think about like the architecture of a database system and trying to separate all the different layers of a traditional vertically integrated database system, building open protocols and open standards to connect those pieces with each other to enable interchangeability so that we can start doing it. Maybe if somebody comes along and develops a better storage format, then we can incorporate, and maybe that storage format only works well for certain types of use cases. But you can choose to say use Parquet files for one set of use cases, whereas now there's new file formats which are specialized for multimodal AI data, including images and video, like the Lance format. And so you'd like to be able to take advantage of those new developments in the ecosystem without having to do a full tear out of your system and basically throw the baby out with the bathwater in order to get access to new functionality in one layer or new or enhanced functionality in one layer of the stack. If that makes sense.
It does. What I'm curious about is how this interacts with the more traditional closed source database and analytic software providers. Have you found support in that, or is this felt like competition? How do you get folks like that on board? Or is that not even a consideration and it's really just, a kind of orthogonal standard?
Well, I think it's one of those, like, the open source model succeeding stories, in the sense that a lot of the adoption and growth and success of the composable data stack, so essentially Arrow, DuckDB, Data Fusion, and a collection of related open source technologies, has been really driven by open source adoption and grassroots bottom up adoption and pressure on some of the larger more powerful forces in the ecosystem. And so Data Fusion, for example, is a modular customizable columnar query engine similar to DuckDB. It's written in Rust, but it's really designed for customizability. So rather than being a batteries included ready to go system, which is more like DuckDB, Data Fusion is meant to be customized. So it wants you to mess around and modify and add operators to its logical planner layer. It wants you to be able to hack on the optimizer to introduce new features in its SQL dialect. And the idea of Data Fusion is that you could have this off the shelf high performance Arrow native query engine and use it to build your custom database engine or your custom query processing solution. And as time went on, Data Fusion just got more and more popular. It got better and better in terms of performance and extensibility, to the point where Apple decided to go all in on using Data Fusion to build its Spark accelerator layer called Data Fusion Comet. So now there's a team at Apple building, Spark, accelerating Apache Spark with Data Fusion. The creator of Data Fusion Andy Grove, works for Apple and leads that team there. But that was something where it wasn't a top-down thing necessarily, but rather like people looking in on the evolution of the data stack and seeing like, okay, these technologies are becoming integrated like all over the place, and they're getting better and better over time. They're attracting more and more contributions from the open source ecosystem. And it's better to get involved in these projects, hire people to work on them, and influence their direction in a beneficial way, rather than go some totally different way or build something that's completely proprietary. I think another thing that is driven the adoption of these composable data stack technologies has been the trend in open data lakes, or what is now called like the lakehouse architecture, where you have a structured data lake, scalable metadata store like Apache Iceberg. So you can think of it as like an evolution or a formalization of some of the ideas from the Hadoop era, where originally the way that data sets were managed and their metadata was managed in Hadoop was you store the data in HDFS, and then there was a metastore called the Hive metastore, basically a MySQL or Postgres database that contained all of the the details about like what constituted a table, and whenever you were planning a query, you would read data from the Hive metastore, and that would tell you what files you need to read to be able to run a particular SQL query with your chosen compute engine. But Hive ran into scalability challenges, especially in very large data lakes. And so that led to the creation of these new open data lake or lakehouse technologies like Iceberg, Hootie, and Delta Lake, which present a more scalable and high performance approach for some of these really massive data lakes that you find among the biggest companies in the world. So it's been interesting, but again, it's a success of the open source model, and I think also, to see cutting edge research like CWI, the birthplace, one of the birthplaces of analytic columnar databases, basically CWI and MIT and a handful of academic database research labs. They chose to build a research group there, chose to build DuckDB as an open source project. They could have gone and built another analytic database company and build another commercial analytic database, but they chose to build a SQLite type system for analytics to be, one of the best batteries included embeddable SQL engines out there. And now, they have a project that is open source, has massive adoption, and you'd be crazy to go and build a brand new embedded database engine from scratch now. Like, either you need something customizable and you want to work in Rust so you can use Data Fusion. If you want something that's batteries included and ready to go out of the box, you choose DuckDB. And that's, what we're seeing kind of across the board.
Yeah. So the open source strategy ultimately sort of trumps because it allows for a full range of highly customizable through to, as you call it, batteries included or fully functioning. So let's shift the conversation a little bit and not totally cast our eye forward, but maybe cast our eye to the present, which is this whole idea of building on top of this stack, how people generate insights and conclusions off this data. There's maybe a working theory that there is no future for data scientists and data engineers because smart models, and being careful not to say LLMs, but maybe LLMs are going to become so good at understanding and working with data that the notion of asking an analyst to tackle a problem will seem silly, and rather we'll just ask our smart agent to figure it out themselves. And you have a bit of a contrarian view here. And my sense, but I don't want to lead the witness, as it were, is that it comes from your experience in dealing with tabular data with complex business logics in both pandas and Arrow, and just trying to connect what we were just talking about to this challenge. So talk about, let's start with the question of whether you think we're on the verge of firing all the data analysts and turning it over to, ChatGPT something or whatever. And then maybe, let's start there. And then we can talk about, why or what about tabular data?
Yeah, there's a lot to that question, many layers to unpack. Well, first, one of the things that I've observed is that maybe one of the dirty secrets of the term data science, and maybe why we're hearing the term data science and data scientists thrown around less and less these days, is that a lot of data science roles, or what people were trying to hire data scientists and build data science teams in the early and mid 2010s, is that a lot of those teams ended up essentially doing business intelligence. So doing engineering on data pipelines and doing ETL or reverse ETL or data plumbing, and ultimately to create a dashboard or a series of dashboards that could be updated. So it was an evolution of the traditional, kind of the old school, BI engineer, ETL engineer building a database to power, somebody's Tableau server, Tableau instance. And so I do think that a lot of that work, the mundane building of dashboards and allowing business users to, with natural language, to ask for custom, like, bespoke dashboards that answer an exact question that they need. I think increasingly that work is going to be done more and more by LLMs, especially as there's a lot of work happening recently on semantic layers, which are something that's, I think, frankly necessary in a lot of cases to make LLMs effective at being able to reason about the relationships between tables and to be able to generate correct queries against the data. Without a semantic layer, like, there's lots of examples that have been shown about how LLM can reason incorrectly about the relationships, like the join relationships between tables, and make the kinds of errors in writing SQL queries that a first year analyst writing SQL would make, double counting and things like that. But I think that ecosystem will become more mature, that semantic layers will become more widely deployed and standardized. More and more of, like, that dashboard building and custom dashboard building work will be taken care of by agents. But I think there is still data science work, which involves modeling and asking nuanced or subtle questions that require, like, judgment and intuition about the having domain expertise and understanding of, like, the business context where the questions are being asked, and choosing the right techniques to be able to build a statistical model or a machine learning model. Maybe you're trying to determine a causal relationship or do some type of forecasting, and a lot of this type of data science work is more, it's part science and part art, and relying on experience from past modeling or statistics work. And I do think that a lot of that nature of statistical work in data science still requires a lot of human judgment. And I think will be, maybe eventually it will, once we have AGI, maybe it will be taken over by an AGI statistician. We'll see. But in the short term, I think there still is a need for that's one of the areas where there's the most human judgment needed. Where if you just turn over all of that work to an agentic data scientist, it's likely to run into pitfalls, or only explore the types of questions or analyses that the LLMs are well suited for. And so the more complex, there might be some study that you need to run that might require dozens of queries to be run, and the results need to be, like, stitched together and compared in lots of different ways. And LLMs are still at a stage where, like, they often struggle to count. And so asking them to reason about, like, you ran these 35 queries, and we need to stitch together the results and then reason about them. Right now, like, a lot of that work is being offloaded to tool calling, because LLMs are not great at looking at data sets, which we can talk more about. But we're still, I think we're still at early days in terms of data scientists being put out of a job by AI agents. But we'll see where things land in a few years.
So I want to maybe make this super basic. It strikes me that large language models, I mean, the answer is in the name. It's a language model, and language by its nature is sequential. It also has these slightly arcane rules. I mean, all languages have a grammar, et cetera. And they are decidedly not tabular data. And they're not really even code. So, like, to the extent that we believe LLMs are good at writing code, for example, code is a much closer analogy to language. In fact, it's in a way a simpler version of language, because it has a very tight grammar, a very tight syntax, whereas as many people are learning the English language for the first time will note, there's lots of poor, badly implemented rules in languages. Whereas tabular data it has very specific set of features that LLMs are just not at all competent with. And
Right.
you gave a very simple example of counting, but even simple notions of sorting and clearing and filtering and like basic behaviors are things that are just a mystery to it. Am I framing it fairly?
Yeah. I mean, I think I haven't run any studies myself or set up structured evals to get the data for myself, like the accuracy results. But I remember early on, I think it was in the Claude Sonnet 3.5 or maybe Claude Sonnet 4 era. I built a little system to collect and summarize data from Git repository history, and it would create little tables, and then because it was a lot of data to summarize, and then I asked it to analyze the data that was summarized in the tables, and it would struggle to do basic arithmetic in combining really small tables of data together. And so that was the first time that a light bulb went off in my head. I was like, oh gosh, like this, these models, like they're for language, they're not, they struggle to do things like adding or combining data sets unless all the work is delegated to tool calling or writing Python. They'd be better off writing Python code to do the work than actually trying to do the arithmetic or the logic in the language model, themselves. But yeah, you're absolutely right. And there've been some research lately around the retrieval problem. So basically, the idea of the retrieval problem is if you present a table, let's say a spreadsheet or a table of data, let's say it's like students in a class, and then there's a bunch of columns about attributes about those students. And so the idea is that you ask the model for this student, could you tell me, let's say every student has 10 attributes which are stored in the table. And you ask the model, like, can you tell me, like, for this student, like, what is their attribute C or their attribute F? So just essentially looking at the table and straight up looking up the value in the table. And the frontier models have gotten to a point where they have high accuracy, over 90% accuracy in the retrieval problem. But the smaller models they fail catastrophically at this retrieval problem. And I'm blanking on the name of the blog post, but there have been people that have done studies, like even trying to determine what's the best data format to present a table to an LLM, especially the smaller, more efficient, cost-efficient models, to get the best accuracy for the retrieval problem. And it's unsurprising. It's a little bit surprising, the results. Like you would think that like CSV format would be a good format for an LLM to look at the data, but it turns out that amongst the 10 or 15 different ways you could format a tabular data set, there's some weird formats. Basically markdown key values, I think was one that I saw, which was a format that I'd never heard of. I think it was invented for the study, where it turned out that like, presenting the data in this like markdown format with like each row as a markdown section would yield better retrieval than putting the data in XML or in JSON in the prompt. So I mean, I think some of it I suspect, I mean, I'm not an AI scientist, but some of it may have to do with like the autoregressive nature of like the next token prediction, design of these models. And so I'm sure that they'll get better over time, but these large frontier models are really expensive to run. And so, the hope is that as LLMs advance, that the small models can become more and more effective, where we can run the model at the edge on our phone. Or I just got myself one of NVIDIA's DGX Spark, AI, sort of little AI mini computers to experiment on and to build some of my own fine-tuned models. And so I'd be really excited if like, we could do really great work at like, model, like with local LLMs, not requiring, $30,000 or $40,000 GPUs, but to really get the performance, you've got to run on these super expensive, these really expensive hardware configurations. And so the to get cutting edge inference is quite expensive these days. So it's an interesting problem. I think there's a number of companies that are working on foundation models specifically for tabular data. basically an AI approach to like prediction and forecasting and regression and things like that. And so I think we'll definitely see more interest in that area. I'm surprised that the frontier AI research labs aren't. Maybe they've got internal research projects that they haven't announced, but maybe as some of the hype shifts away from chatbots, more work might shift towards building foundation models for tabular data, because ultimately, like, a lot of the value in business data sets does lie, and a lot of the value in, value to unlock for businesses does lie in their data. And so to get the most value out of AI in a business context, like, somehow we've got to reconcile like this incongruence between current generation LLMs and interacting with tabular data sets. Even like MCP, which was developed to provide a standardized interface for LLMs to interact with external systems and tools, not an especially efficient way to expose data to an LLM. Even if LLMs were good at looking at, even if LLMs were really good at looking at data sets, like, MCP is not the interface that you would want to provide, 100,000 row table to a model to look at. And so we're far, just thinking about all the work that we've done, like the engineering work that we've done on Arrow to achieve high performance, interoperability in all these contexts. And, the AI equivalent of like, how do we expose data to an LLM, looks like caveman tools, by comparison.
Well, which is exactly the connection I was hoping you would draw, because it's like we've done, 10, 15 years worth of work to make data, to use your example, to make data interoperable. And then we turn to this new world and we just start from scratch. Like, it doesn't make any sense.
Right.
Also, I was going to ask you, the other, it seems to me, a failure point with these models is that they aren't deterministic. Like, the one thing we can say confidently for any analytical problem is that if you run the analysis twice, you should get the same answer. Like, it's not okay to be like, well, it's sort of around 2, like, or today it's
Yeah.
2 and tomorrow it's 20. And like,
Yeah.
whereas that's actually a feature, I think, of these language models, which is, obviously you can adjust the temperature, but I think something people like about it is that it gives you different answers every time. Otherwise, it's just a rules-based system. But I don't know if that resonates with you.
It does. I mean, initially I throughout all of last year, I was pretty AI skeptical. Let's put it that way. And this year, I think in part because the models have gotten a lot better, and also the emergence of CLI coding agents like Claude Code, I think have really, for me, that was a big unlock where, working, like, I wasn't particularly enthused about using the, AI IDs like Cursor and Windsurf, but I think within a couple of weeks of using Claude Code to delegate mundane coding work, refactoring, just stuff that was taking up my time that didn't seem particularly high value, and seeing a lot of returns on my, like, really quick returns and productivity benefits. I've, become a big believer, and now I use Claude Code almost every day, and definitely costing Anthropic money on my max plan because of, the couple billion tokens that I consume every month. But at the same time, like, the imperfection is, it, like, if you don't observe, like, see the inconsistency or the non-determinism, like, it is problematic, especially for data work where you need to have an exact answer every time you run the system. And so even the risk that, like, the model, if you have the model call tools and you're leaving some interpretation of the results to the model, and one day you get one answer and another day you get, from the same input, you get a different answer, that could lead to a business decision being taken that is detrimental to the business, and that is problematic. And I often find myself playing whack-a-mole with the prompts to get consistent behavior out of the models, like, particularly like creating a consistent development environment where each time I pick up Claude Code, that I can count on the agent to predictably do the same things, whether it's like mundane things like making sure that the style checks run, and like, but it seems that 20 to 50% of the time, like from day to day, like without modifying the prompts or the Claude.md or any of this stuff at all, like, the next day I'll open Claude Code and it will forget to, it will forget to do things. And I'll say, hey, you forgot to do this. Like CI is failing. They're like, you're absolutely right. I ignored your instructions that we wrote in Claude.md. And so the idea that these tools can just like casually, forget things that, even with their massive context windows, like they have the memory of a goldfish. And so, I'm sure that it will get better. And, again, like I use these tools every day. Like they bring a lot of value for me, but I'm also not quite, drinking the Kool-Aid and believing that like, this is the next great step for humanity that's, going to lead to a world without work.
Yeah. And I mean, maybe to say it in a really simple way, I think you would agree that it's made you much more productive, but it's not made you obsolete.
Yeah, no, if anything, like my experience building software feels essential when I'm using these tools, because if I wasn't able to read the code to review it as though I was reviewing the work of a junior developer and tell it all of the things that it messed up, its architectural problems, like the incorrect or missing unit tests, like, incorrect documentation, incorrect implementations. Like I have a lot of experience reviewing other people's code. And I feel like that is one of my biggest assets when I'm working with these coding agents, is that I tell myself when I'm working with Claude Code, like treat all the work that is coming out of this agent like a very motivated, very productive junior developer who's prone to errors and doing things and frankly creating messes. And so I, at a glance, like to be able to spot design architectural problems, things that need to be refactored, code duplication, code smells, all that feels essential to getting the most value out of these tools. And I've heard, from talking to other people, that the people that are the users, the AI users who are able to get the most value out of the coding agents are the most experienced developers who are able to bring their experience and judgment to give, not only to write better prompts, to be very specific and articulate about what you're asking for, but also to be able to judge the output and give high quality feedback so that you can corral, basically move things in the right direction to get what you want. But I do think that we're likely to have like a vibe coding epidemic of like, kind of amplifying Dunning-Kruger syndrome of people building software, AI slop, not reading the output carefully, not doing code review, basically just letting Codex or Claude Code do its thing and then slapping up a pull request without giving it a second's thought. And, there's likely to be, substantial business losses because developers are deploying vibe coded software into production without sufficient code review. Of course you can, protect yourself against some of this by taking a test driven development approach and asking the agent to build a test suite that of course you have to review before you set to implementation work. And, in the past, like I was never really a hardcore test-driven development, TDD adherent, but now using coding agents, I've become much more so, because each time I sit down with Claude Code, I treat it as a defensive exercise where it's like, how do I protect myself from the agent doing incomplete work or insisting that it's completed the problem or solved the problem in the way that I asked for, but is, it's deceived itself into believing that it's finished the problem. And so the more test coverage, whether it's, test coverage, automated checks, benchmarking suites, like all the defensive things that you would need to do already to create a piece of production software, it's even more important to do that with these agents. Otherwise, just any software that they create becomes a huge liability otherwise.
Yeah, I think that's a wonderful insight, actually. Like it's like these practices become more important because you're, and I also want to loop it back to something you said before, which is the future is a smaller number of really experienced, thoughtful architect engineer types marshaling a army of these agents, but then to your point, layering in this defensive coding practices, maybe that model starts to feel closer to the future. I sort of am waiting for the first spaceship crashing into Mars due to a vibe coding error, as
Yeah,
opposed to a units
yeah,
conversion problem.
right,
Um,
right.
yeah,
Yeah, it's interesting. I think one of the existential problems is how will junior developers become senior developers? And so the old working model was
right.
that you become a senior developer by doing junior work over a long period of time, getting good at not only writing code but reviewing code and seeing what good code looks like. And then as your career progresses, more of your work transitions from maybe as a junior developer, you're doing 90% writing code, 10% code review. Maybe a senior developer is doing 10% development, 90% code review. And so now delegating more of the coding work to these agents means that more and more of our work is shifting to code review. And I think that code review is still going to be a bottleneck. And so even having a senior developer with an army of AI agents, who's going to review all of that code? I mean, you can have the agents review their own work, or you can,
Well,
like I
good luck
have,
with that.
yeah, I mean, I have, I have friends that have told me about having, Claude Code implement Codex review or vice versa. Basically, use the agents to review each other's slop and to make it better. But yeah, I think to have a smaller, I do think on the whole we're going to have fewer software engineers, and especially really experienced engineers will spend more of their time reviewing the output of agents. But still, there's a human bottleneck of being able to do code review and assess the work and determine whether or not it should be accepted, or whether in many cases, like these AI generated pull requests and patches should just be thrown out altogether and start over. But one of the nice things is that the cost of starting over is so much smaller. And so if you see some somebody approach a problem and they've it's basically like the Panama Canal approach versus like going around, the bottom of South America. And sometimes like, with an AI agent, you can generate an impressive amount of code, like thousands and thousands of lines of code in an afternoon to hack your way around a problem. But maybe there's a more elegant solution that the AI agent just didn't see, or like wasn't obvious, from given all the data in its training set, to see like the simpler, more elegant solution. And so if everyone is, if everyone is like always using the agents and creating solutions, which are sometimes circuitous or kind of missing like, the more elegant, more maintainable, more sustainable approach, that's going to lead to these projects where, you have 100,000 lines of code that maybe should only be 15 or 20,000. If written by a human, it might be a much smaller code base that's easier to maintain and is more robust over time. Whereas, with this large code base, you start to reach a certain limit where it's even having the agent look at the code base starts to become unwieldy, like files with thousands of lines, like it starts to choke on the input pretty quickly. Like I recently created like a little personal finance tool with Claude Code called Money Flow for interacting with like, I use Monarch Money, so a personal finance tool. And now I have a project that I created from scratch with Claude Code. So it's 95 to 99% created with Claude Code with a lot of feedback and code review from me. And it's pushing, including the test suite and all of the infrastructure and everything, it's pushing 40,000 lines of code. If I'd written it by hand, probably would be a lot smaller, in part because, I couldn't spend nearly the amount of time that it would take to write a code base that large. And I would have cut more corners or made simplifying assumptions in order to accomplish the same things, like with a lot less code. So
Yeah.
so it's interesting, but yeah, I'm learning day to day, and I'm no expert by any means, but I feel like the more I use these tools, the better I understand them and the more I get out of them.
Well, Wes, really appreciate you taking the time. This was a bit of a journey from where you started and through to the present day, and also thinking about what how to think about at least a future where we're marshaling agents on our behalf. I really appreciate you taking the time and sharing your thoughts and insights.
Yeah, thanks again for having me on.
Thanks for joining us for the latest episode of the Data Masters podcast. You'll find links in the show notes to any resources mentioned on today's show. And if you're enjoying our podcast, please subscribe so you never miss an episode.